my Christmas. Is this question on equilibrium? Since Christmas, we are here to send my gift. I'm giving my own gift this afternoon. Is this chemical equilibrium? So let's look at it together. Even though it's a gift, as we open it, we'll talk about it if it is acceptable. So let's look at the chemical equilibrium question together. I believe my gift will be acceptable. So 0.025 mole of hydrogen iodide is added to a closed vessel and left to reach dynamic equilibrium. The total pressure of the vessel is 100 kilopascal. Reaction equation: 2Hi gas reversible to give H2 gas and I2 gas. Explain what is meant by the dynamic equilibrium. 2 marks. What will be your response for that question?
I would say that the reactants are continuously forming products as products are continuously forming reactants in fixed concentrations.
Okay, so you will tell me that rate of what?
So the rate of forward reaction is equal to the rate of backward reaction.
Yeah, is equal to a. That will be 1 mark. What will be second mark?
They'll be in fixed ratios or concentrations, like both the reactants and products.
Okay, so concentration remains constant. Okay, that appears to be bonus. No. Describe one difference in the initial appearance of the reaction mixture compared to the mixture at equilibrium. You look at this initial. One difference in the initial appearance of the mixture compared to the mixture at equilibrium. What does initial look like?
I think it's more purple in the reaction mixture. It is purple, like the color.
Okay, why did you say it purple? Why did you say that?
Because there's more of the hydrogen iodide in the reaction, like the concentration of Hi has increased. So,
hydrogen iodide is colorless, so this one is purple.
oh, okay.
So it is purple. So mixture will be purple. That's correct. So mixture will be purple. So as the hydrogen iodide decomposes, the mixture is purple. Before it will get to it, the mixture remains purple. Okay.
Oh, I think it said Hi was colorless.
Yes, Hi is colorless, but it's a mixture. They call it mixture now. So the purple color will overshadow the colorless Hi. Because they said before the mixture gets to equilibrium. So the initial there is not when there was no reaction. So they are talking about initial appearance of the reaction mixture compared to the mixture at equilibrium. So mixture before equilibrium is purple. Yes, because we have colorless stroke purple put together. So overall, it's still going to be purple before getting to equilibrium. Then when it gets to equilibrium, the purple color will be kind of evenly distributed, simple as that will be evenly distributed. But before it gets to that, since small amount of purple is there, it will overshadow the colorless hydrogen iodide. So that is correct as well. Okay. All right. Let's look at this verse. What this verse? What if you got three? What if you got three? Don't mind me. We're not in church. What if you got three? Write an expression for the equilibrium constant. Yeah. Since we have our since we're having what is it called now? 2HI reversible out to give me I2 plus H2. What we are keeping? Okay.
Sorry, I think I was muted, sorry. It will be P yeah, PI2 plus PI2 times
Okay.
PH2.
Like this?
Yes. Over PHI square.
P what?
PHI square.
Okay.
Not like that. Like the square will be same. It doesn't matter.
Okay.
Yeah.
No, you are supposed to. See, you didn't mean that it should look like this. It should be like this.
Yeah, that's what I thought.
Okay. Both of them are correct.
Okay.
All right. So that was under mark. All right. So at equilibrium, the partial pressure of HI is 86.4 kilopascal. The partial pressure of the reaction is 86.4 kilopascal. Calculate the amount of HI present in the mixture at equilibrium. Show your working. I don't know how many marks. This should be 2 marks anyway. This should be 2 marks. So at equilibrium, the partial pressure is of HI. You're like saying that equilibrium Kc is this one. So we are given the no, this one is just ordinary partial pressure. That the mole is like the mole of so how do we calculate the amount of HI present in the mixture at equilibrium? And I don't like the language. They say show your working. Whenever they say show your working, it means that they mean business. So we both look at it together. So
Did they give the total pressure before?
let me go back to the question. We're given the total pressure to be 100 kilopascal.
Yeah.
So the total pressure is 100 kilopascal.
So is it that do we use the ice method or we can just use another method to get it?
You said what?
Can I use the ice method or is it too
Anyone,
long? Okay.
any method you are okay. Any method you can use anyone. But
Okay.
for your AS, if you want to make things organized for yourself, you do your ICE table. If you do your
Okay.
ICE table, so you will be able to get things organized. So if you do your ICE table, 2HI, 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 and we have I2 also have H2. So I haven't said that.
So
What are we given? Yes.
the initial concentration is 0.025.
Okay. So we have 0.025. 0.025. Okay. So 0.025. So here will be
Then
0. Okay.
yeah,
Mhm.
0, 0. Then you now for under HI you put minus 2x as the
Okay.
change in concentration.
Minus 2x for change. Yes.
Then for I2 you put plus x.
Okay.
Then for H2 you put plus x as well.
Okay.
So at equilibrium you
Yes.
have 0.025 minus 2x.
Okay.
Then yeah, then x, then x.
Okay.
So I think you can now find the mole fraction for mole fraction.
Move power.
You can find total mole.
Okay. Total mole will be what now?
Total mole will be um 0.025. Yeah, 0.025 basically. Oh
Okay,
no,
that
no, no.
okay,
Yeah,
that was
yeah,
total. Is that the total mole?
yeah. Total mole, yes. Because
Okay.
when you add everything together, the
Okay.
x plus x will be.
Okay. Because minus 2 plus 2 is that will be 0. Okay. That's
Yeah.
good.
So you already have your initial, which is 0.025,
Mhm.
and then you have a total. Um, oh, I think there's a problem maybe. Or can get your partial, okay. Can get your partial. Oh, I'm not sure again, actually. I'm not sure again.
Are you trying to say that what? Okay.
I said I'm not sure again. Like,
Okay.
um, yeah. So, wait, to get partial pressure, you multiply mole fraction by the total pressure, right?
The top pressure is 100.
Yes.
Partial pressure is given to you as well.
Okay, so sorry. You now do, for the mole fraction, you do 0.025 minus 2x
Okay.
over 0.025 times 100 um s- yeah 100 times 10 raised to the power of
Okay.
3
Yes.
times 10 raised to the power of 3.
Is that no, no, no? Your answer will be in kilopascal. So don't put any.
Oh,
Since yeah, your answer should be in
yeah,
kilopascal.
is equals to 86.4.
Okay. 86.4. Oh, so we can cross multiply. So
Yes,
0.025 times 100, that will be what? 0.025 times 100.
that'll
So
be
we have
2.5.
2.5. So we have 2.5 minus 100x equals
Uh,
to,
so it's 200.
okay, thank you. Thank you. Yeah. Okay, so we have a minus 200 equals to
Two,
0.025
yeah,
times 86.4. That
that
would be
is 2.16.
2.16. 2.16. Is that all about? Okay, let's look at then. What do we do next?
So you now take the like terms. So it'll be 2.5 minus
All right.
2.16.
All right. So 2.5 minus 2.16. So 2.5 minus 2.16. So we have 0.34. So
Divided by 200.
yes, 0.34 divided by 200 equals to x.
So x is equals to 1.7 times 10 raised power of minus 3.
Okay, that will be 1.7 times 10 power minus 3. And that will
Yes,
be 0.0017.
1.7. So you now subtract that from 0.0. You do 2 times
Okay, subtract it from this
1
one. So 0.25,
times 2
0.025, so 0.025 minus
times 7.
point zero zero 17, 0.025 minus 0.0017.
Yeah, I got 0.0216.
What do you get?
0.0216.
Okay, so the mole of HI is 0.01 what?
0.0216.
Okay, 216 to 2 decimal places. Oh, it's okay like
So,
that. It's okay.
okay.
Yeah, it's okay like that. How do you see the question?
The question was okay. It's just that when I reasoned it more because of the assignment, I looked through the correction and I saw that I could have done the same thing using the ICE method. So I think I just had to reason it again. It took a bit of time.
Okay.
But overall, so we have a question.
Yes.
So the mole fraction, right? It's the mole fraction, you always use the total moles at equilibrium, right?
Yes. 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 Most questions
Total mole.
it will always come to equilibrium. When you get to 100 level, you can they begin to give you a question that on 20 level they give questions to solve before equilibrium, during equilibrium, after equilibrium, forward reaction and backward reaction. But for now, they are laying in your they are just what they are laying what you're asking to know is about how to handle equilibrium problem either for forward reaction, maybe backward reaction. But later, if you are doing maybe assuming you are doing OSSD, OSSD,
Yeah,
OSSD,
the Canadian pathway.
OSSD, then they in their own they will do before equilibrium, during equilibrium, and after equilibrium. But A level is basically just most cases equilibrium. It's not going to go beyond that. And it's an AS question. All right. So let's move on to this work. Okay. Now today's work. Okay, let me see. All right. Okay. So that is a very good question. Now let's look at the overview of what we learned under under substitution reaction mechanism. We have the 3 steps: the initiation, we have the propagation and termination. You must know that the propagation is always double. It's a double step. There are 2 steps there, and that initiation is just 1 step. It's 1 step. While termination, there are always 3 ways to terminate a reaction: organic, reaction substitution. There are always three reactions that can lead to the termination of reaction. So one of them is what we need, just one of them. And if you know the three of them, very, very important. So here we look at the first one, which is initiation. Under the first one, they call it radical being created. You create radical. So it occurs through your homolytic fission, where the UV light, the presence of UV light, will provide the minimum activation energy to break the bond into two. And I think that day you were asking me, should we always put something there, like the chlorine to chlorine bond? The UV light providing energy breaks the covalent bond, and the electrons comes on chlorine like this. So learn how to do that. If you don't, sometimes they can ask to do, this is an equation. This does not really show the mechanism. It's showing the equation of reaction. But if you are asked to show the mechanism, your initiation step must go in this form: Cl dot plus Cl dot. Then you do it this way, and then to show, because it must have curly arrow showing the direction of the shared electron. All right, that is very essential. So that after that, then you have the radical created, and we said that radicals are species with odd number of electron, or species with uh, unpaired electron, anyone. So it's very important that we define the word free radical. So a free radical is a species. It's never a molecule. It's a species with unpaired electron, or a species with odd number of electron. And then you should also be prepared for the structure of any free radical. So your Cl dot, this is the formula. The structure have to show that there are odd number of electrons in this form, 7 of them. So we have this one. So I haven't done that. So we have two chlorine-free radical. Chlorine-free radical. That is the name. All right. So we go to the propagation step. So the chlorine-free radical is very reactive, and because it's very reactive, it will dictate the direction of reaction. So the chlorine-free radical, will, the direction of the arrow will come from, we are going to do it this way: Cl dot plus H. The bond we are breaking will show it, then CH3. Since we are breaking that, so it can go this way, like this. So the arrow comes from the dot. Don't make the mistake of allowing the arrow to come from chlorine. Like this is wrong. If you do it this way, like this, it's wrong. It will not score. So when you are asked to show the mechanism, let the arrow come from where the dot is, because the curly arrow tells us the direction or the pathway. of the action or the reaction, shows us the direction of the intermediate reaction taking place. So if you do it this way, it's 0. So because they know what they are looking for. Candidates should use the calling arrow to show from the dot. Okay, so having done that, it will break the covalent bond, and then because hydrogen is the H dot is lighter, so you're going to have HCl formed plus dot CH3. So this is a methyl free radical. Methyl free radical. Okay, and so we have been able to show the formation of hydrogen chloride gas. This reaction continues because a free radical is still available. So the free radical being available, which is dot CH3 dot CH3, will now react with Cl hyphen Cl. So the second propagation step. So the arrow will come from the dot again. The arrow comes from the dot to break the covalent bond. And so we'll be having dot CH3 attacking Cl dot. So we have CH3 Cl plus Cl dot. So these two steps are major steps in the mechanism. The first step is your initiation, and these two steps called propagation steps. So we have been able to produce chloromethane. You will see that in each propagation step, we have produced something. And you can use this method to produce HCl or CH3Cl because there are a lot of other fragments being produced as well. So those fragments are difficult to separate or to remove. Therefore, this mechanism does not lead to producing um, um, bulky amount of HCl or bulky amount of chloromethane because there are other fragments being produced also during the reaction. As you can see that in the termination step, you have Cl to produce, and also produce. So all this one will not allow you to have a pure form of chloromethane and hydrogen chloride gas. So then we have the termination step now. The termination step, like I said, there are three of them. To stop the reaction, the first thing that must come to your mind is that the radicals, if you can remove them, then the reaction will stop. The radicals are this one and this one. So the two free radicals there. If you can remove them. So the first thing is CH3 dot combined with Cl dot. So that gives you CH3Cl. Either of that, because those are the two free radicals, or if Cl dot will react with another Cl dot to give us chlorine, or CH3 dot combined with another CH3 dot, and that will give us what? C2H6. Any of these three will give us, will stop the reaction because it leads to the removal of reactive species. Okay, so overall reaction now, we can only go for 4 of them. So the 4 of them, let's list them. This is number 1, number 2, number 3, then any of this one as number 4 for the reaction mechanism. Now, haven't done this. This is the simplest example of free radical substitution reaction. Um, under the under the propagation step, you saw radical used and radical regenerated. So in your exam, they will ask you which step is radical being used and radical being reproduced, propagation step. So which step is radical being removed, termination step, and so on and so forth. So like I was saying, that this is the simplest example of of substitution reaction mechanism. And in your introduction to organic chemistry, we have display formula. We have learned displayed formula. What again have we learned?
Stru structural formula.
Okay, structural formula. Yes, what
And
again?
also skeletal. The skeletal parts, like the only thing I'm not sure about is how to do isomers of the skeletal.
Okay, isomerism for skeletal,
Of the
Sabi.
skeletal, yeah, that's the only thing I'm not sure about.
So we'll talk about that. Now, so this three, you could be given any question and you'll be asked to present your answer in any of these ways. So let's take one of them. Let's look at skeletal formula, because that one can be like that one. As in, when I say like it, they really like this question, this part of the of your syllabus. Skeletal formula. Let's look at the one for skeletal. Okay, let me get you an example. Okay, let's see the example I'm going to give you now. Okay, all right. Okay. Now, under skeletal, assuming you are given, let's look at this molecule and you give me the name of this molecule. What does this molecule give you? What's the name of this molecule?
Butane, cyclic butane,
Okay,
cyclobutane, sorry.
cyclobutane. What of this one?
Cyclopropane.
Okay, cyclopropane. So this one reacting with chlorine will give you good. They now ask you to describe the mechanism. Yeah. So this
So,
one will be challenging a little bit for students who want to be going with the other structural formula. Okay, let's start. Let's start with the initiation. So we're going to have Cl.Cl. So we have this, and you have that. So what will be the overall answer? What will be the next answer?
um, Cl dot, 2Cl dot.
Okay. So we're going to have CCl dot. Okay. And coming. Okay. So we're going to have, you said we have 2Cl dot, that's termination. Sorry, that is initiation. Okay. So we have a Cl dot plus this one. What will be the answer?
Um, HCl plus CH2 dot.
Plus what? Like this?
Oh, No. Yeah, yes.
So you put a dot there.
But
That is that. So we have
yes.
this one. What will you call this one? This is iodinic gas. Yes. So will now be what? The name.
Cyclobutyl free radical. Butyl free radical. Yeah. Cyclobutyl free radical.
Cyclobutyl
Butyl free
free.
radical.
Okay, free radical. That's good. And then the second step, that will be this plus Cl dot Cl. Remember here is like this. So the arrow comes this way. Okay. All right. So the same thing, the dot is there. So it can come like this. What do we get?
Um, you get C the same thing, the rectangle with a CL.
Okay, good. With a Cl plus what?
CL dot.
Dot. What do you call this one?
Um cyclochlorobutane.
Cyclochlorobutyl. Okay, that's correct. And then we have gotten the first initiation step, the two propagation step, and we are going to termination step. Give all the termination step. The first one will be what?
CL dot plus CL dot two
Cl
CL
dot to
to
give
give
what?
you CL2.
Cl2. Second one.
Then um CL dot plus CH3 dot
No, it's the rectangle dot.
rectangle dot
The rectangle dot. So or the square dot to give us what?
give you CH rectangle then CL.
And the third one.
Then two CH3 dots
Okay.
will give
Come again.
you
Two what?
two rectangle dots
Oh, yes. Ah, two rectangle dot.
give you will give you what's it called? A an octagon.
Is it like this?
Will give you what's it called? You use skeletal formula 1, 2, 3, abi? Or you just use cyclo
And look at
sa
is my diagram correct? Are you seeing my diagram?
oh yes, I'm seeing your diagram.
Is it correct? The product.
Um I think it's okay, but like I would have if this was an exam question, I would have drawn an octagon.
Octagon. No,
Or
no. Okay.
is that
Um,
but I know it's probably wrong. So I'm just saying what's
yes.
like I was read.
Octagon. That one will be that one. It's a straight chain. If you draw octagon, are you sure it will be the same thing? Because this is the answer. Let's compare it with the octagon to see if it will be correct. Octagon like one like this.
It'll be too much, don't worry. It'll be too much.
I think I'm with one, two, three, 4, 5, 6, 7. This right like this one, Abby.
No, because like that there are going to be 8 carbons. So like you have to have
Okay,
more much.
okay, like this.
Yeah, I'm talking about the
Yes.
cyclo
This one?
octane, cyclooctane.
Okay,
Um,
okay.
yeah, cyclooctane.
That one will not be correct
Okay.
because you are talking about one free radical joining another free radical. In the let's look at it closely. The other one was ClCH3 dot plus CH3 dot like this, and we now say C2H6. Um, this one, let's break it down. See, this is 1, 2, 3, 4 carbon. That's C4H7 dot, yes, C4H7 dot plus C4H7 dot. So we're going to have that. So we're going to have C what? C8H14. I think that would be what? Is that what we're saying?
Yeah, that's what I was saying.
Okay. You know that your answer was given to you. Even this answer is correct, but you are to express your answer using skeletal formula. So if you turn your answer to this one, you will not score it because you have deviated, even though it is an answer, even though it is correct, but it's not well presented. So C8H14 is correct, but you are not asked to use what is it called now? Molecular formula or structural formula, because you can actually express this one with this one or using structural formula as well. But so you must know the form at which you have to present your answer. That is important. Okay. So that's just the difference. Otherwise, C8H14 is correct. 2, 2, 2. Yeah. That is correct. So that's about that. Is that okay?
Yes, sir.
Okay, so let's look at the next question. The next, okay, all right. So let's assume that we are done with that. So we go into the third reaction of alkane. The first one was combustion, which can be complete combustion and incomplete combustion. The second one is your reaction with halogen, alkane reacting with halogen, like fluorine, chlorine, and bromine iodine, which is a substitution reaction mechanism, your reaction which has a mechanism. Then the third one is cracking. Cracking is a chemical process. Cracking is an industrial process for converting less useful product, less useful organic product to a more useful product. The less useful product, we call them heavy fractions. There are some petroleum fractions that are not in high demand in the world market. For example, kerosene, nobody is using kerosene these days, but uh, alkenes are of higher demand. Alkanes like methane, cooking gas, ethane are of higher demand. So lower fractions are of higher demand. They have more value for money, unlike kerosene and other higher fractions. So heavy fractions are less useful. So because of that, a method was devised to convert less useful petroleum fraction to more useful petroleum fraction. And that method is called cracking. And then cracking usually involve breaking of the carbon-carbon bond in the alkane. The higher fraction is always alkane, not alkane, alkane. So the alkane fraction, the carbon-to-carbon bond is usually being broken. There are two major products that are obtained when cracking takes place. The first major one is alkene, because that is the one that is of higher value, followed by alkane, alkane or alkane. So the two of them are of higher value, and they will give you smaller fraction like ethane or propane or butane, like that. The mechanism of the reaction, you are not supposed to know it, but let us quickly define cracking itself. Cracking. What is cracking? Cracking is a process of converting petroleum fraction of lower demand into higher fraction, into smaller fraction of higher demand. That's called cracking. So cracking is the process of breaking every fraction. I think I need to write it down. Cracking is not a physical process, it's a chemical process. It's a chemical process. It's a chemical process of breaking large hydrocarbon of lesser demand into smaller hydrocarbon of higher demand. So higher demand in the world market. So cracking is a process. You can remove the word chemical process to save your time. Just it's a process of breaking large hydrocarbon fraction of lesser demand into smaller fraction of higher demand. Simple. Breaking
So,
of heavy fraction into smaller fraction of higher demand. Simple as that. And it can occur in two phases. You can either use thermal or catalytic cracking. It can be thermal. So this place, don't bother yourself about it, that thermal will proceed via free radical mechanism, and then catalytic will proceed via carbocation mechanism. You don't need to know the mechanism. This is the definition and also the chemical reaction that you must know, and the condition. So let's go to the condition for,
so
yes,
would that come out in A2?
is that what?
Would that through carbocation, will it come out in A2 or is
No,
not in A level at all?
you can't even see it at all.
Okay.
It's not part. The only area when you will see that is when you'll be talking about halogen alkane mechanism of reaction of halogen alkane, that you talk about carbocation, and so that's when you will need it, but not under cracking. Nobody, uh, nobody is asking. Nobody will ask you to talk about the mechanism of cracking. It's not in your syllabus. So, but it is when you get to haloalkane, the mechanism of reaction involve forming of carbocation, so on and so forth. Then you can talk about that one. So that is about that. Then we'll talk about now the condition for the reaction. Let's look at thermal first. Under thermal cracking, you will need high pressure. even though the value may not be stated. So high pressure, if you are very bold, just 7,000 kilopascal. So you are sure, 7,000. But simply high pressure is okay. They won't ask you to talk about the value, just high pressure. And the word dama also means high temperature. And this slide is giving you the range of the temperature 400 degrees Celsius to 900 degrees Celsius is high enough. And nobody will ask you about the mechanism. No. Nobody will ask about the theoretical mechanism. No. Nobody will ask you about homolytic fission, but that one is common. Since you are breaking the carbon to carbon, it's homolytic fission. Then what will be the product? Produces mostly alkenes, but alkenes are of higher demand in the world market. Alkenes are used in making polymer, polychloroethene, polyethylene, and the rest. So they are used in making different type of polymers and also alcohol. Then, of course, you know that C2H4 plus water, what will it give you?
You'll give me C.
Is addition reaction. Just add together.
Okay. So C2H6 or
H5, then OH.
oh.
So instead of saying H2, then just put the other ones, you rearrange it. So this is an addition reaction. So cracking, this is ethene with, this is a gas. Okay. So when you heat the two together at around a temperature of 300 degrees Celsius with concentrated phosphoric acid catalyst at a pressure of 60 to 70 kilopascal, you have your ethanol formed in the industry. It's used to prepare ethanol in the industry. So the alkane produced combined with steam at 300 degrees Celsius is actually 150 to 300 degrees Celsius. Concentrated phosphoric acid, 60 to 70 kilopascal, you have alcohol produced. Of course, that is that, and it's an irreversible process. So alkane is of higher demand. So the aim of thermal cracking is to produce plenty of alkane, especially ethene, propane, butane, like that, because of their usefulness in the world market. Very, very useful. Then you can also produce hydrogen. For example, you have C2H6. You can simply have C2H4 plus hydrogen. So hydrogen is also produced. So under the cracking or diamond cracking, the C to C bond can be broken, and also C to H bond can also be broken. So you can form hydrogen, can be formed from there. So hydrogen can be formed. So industrial production of hydrogen comes from cracking of crude oil. When every fraction of petroleum is cracked, one of the major products is also hydrogen. So hydrogen is that. So that is how to get hydrogen in um, in the industry. The other way is more expensive. That is electrolysis. You can get hydrogen from electrolysis of dilute sulfuric acid. That is acidified water. You get hydrogen as well, but that is very costly. But to get hydrogen cheaply, you do cracking. So cracking is it's an essential method of getting cheap hydrogen for making ammonia. So Abba process where ammonia is being made. So what are your takeaway here? The takeaway here is that the definition of cracking, two the definition of thermal cracking. Since we know that cracking is a process of converting heavy fraction into smaller fraction of higher demand, then how can you define thermal cracking from there? Because they could ask you to define thermal cracking. How can you define thermal cracking?
It is the process of breaking large hydrocarbon of lesser demand into small hydrocarbons of higher demand using heat, basically using high temperature.
Yes, yes, high temperature and pressure, and you have gotten the temp. So breaking of higher petroleum fraction of lower demand into smaller fraction of higher demand uh, under the condition of higher pressure and higher temperature. You are done. And so since the two major products is alkane and alkene. For example, let's look at C10H22. That will be decane. So if you have C2H4, like 5 of that, see, plenty of that. How many will remain now? Then plus alkane. More be plus. This is alkane. Alkane. So you have to balance the equation. Let's look at it. 5 times 2, that will be 10. So everything. So let's look at how we can get some. Let's look at it.
Do you just add H2?
What did you just say?
Do you add, oh, okay. When you wrote the 5, when you
Yes,
wrote the 5C2H4,
yes,
I said that, like, do you just add, when you do that, you now add hydrogen, like H2 to
yes,
balance it out?
yes.
Is that
Thank
what
you.
you
Yes.
do?
If you do that, that will be 5 times that will be 10, then 20, you start with plus hydrogen like this. That's when you are making hydrogen. On the other hand, if you are not making hydrogen, C10, H22, to give you maybe C2H4, I have 2 of that. What should be the other product? That will be 2 times 2, 4. Yes, we have
Uh, we did,
C3, yes,
C6,
H8.
C3, oops, sorry, C3,
Will that be correct? So we have 2
no,
times 2, 4. 4 plus 3 is 7. It's not yet correct. This is a 4. It's not correct. If we are looking for, if I put 2 here, will it be correct? So 2 times 8, 16 plus 4.
no.
Okay. C3, okay.
So what are you trying to form?
Yes. What is it?
What are you trying to form?
Where? Yeah.
What are you trying to form? What are you trying to make?
Yes, we have gotten an alkane now. And I said, what would be the remaining product? C2H4 out of
Okay.
C10, H20, H22. So I'm looking, how do we get that? C3H8. So you see, that's what they'll be asking you to do to balance it now. The other one will be an alkane. So let's look at the other options to make it balance. If you use C4, if you use C4, H10, um, H10, okay, let's make it simple. Let's make it simple. So we have 6 remaining. So we have
What was
6H14. Is it? Yes. 6 is H14. Is that correct? C10H22.
correct?
Okay, so 2 times 4,
It's
8 plus 14. That will be 22. 6 is H14. Okay. So, which means that C3H8. No. So, that is about that. So, you should be careful about the product. It is basically, in most cases, alkene and alkane. Alkene and alkane. Except in few cases where hydrogen will be formed. So they'll ask you that this and write a balanced equation. That will be 2 marks for that under your AS chemistry. That's about that. Now, there's one important thing that you must know here. This reaction occurs without air. Air is not part of it. That is it. This cracking of a thing, breaking down of large fraction into smaller fraction of higher value world market, does it occur without air? Air is not there. Air, you don't have air. It is without oxygen. Because if there's oxygen, there will be carbon dioxide and water. So there is no carbon, there is no oxygen. It happens in the absence of oxygen. Very, very important. So that is Dama cracking. Then move on to catalytic cracking. Under catalytic cracking, even you do, like I said, you don't need the mechanism. Let's look at the condition again. The pressure is slight, it's low pressure, slight pressure, slow pressure. You still have high temperature as well, 450, but not as high as the other one. Then you require a catalyst. But they will not ask you to mention the catalyst, but zeolite catalyst, okay, and it will cover electric fission. It's a common thing that you know, breaking of bond in such a way that one of the species goes to one of the 2 electrons is taken by one of the species formed. So usually produces cycloalkane, aromatic hydrocarbon. So you have fraction. I mean, you have a branch product produced and also aromatic hydrocarbon. But nobody will be asking you about all of these until when you get to 200 level in university to hand that you do the advanced one. The zeolite is simply it's an aluminum compound. So aluminosilicate, zeolite catalyst. But they won't ask you about those catalysts, just the fact that it require low pressure, high temperature, and catalyst. So catalytic cracking is process of breaking large hydrocarbon fraction of lesser demand into smaller fraction of higher demand in the presence of low pressure, high temperature, and catalyst. Low pressure, high temperature, and catalyst. Okay, so we leave that. So both of them, alkenes and alkane, even though you are having cycloalkane, even though you are having cycloalkane here and aromatic hydrocarbon, they will not stress you beyond alkane and alkane. Okay. All right. So we're going to the chemistry of alkanes. But before we go there, we solve some problem under alkane. So I'm going to remove this slide and bring in another slide where we can just look at some question and then we can continue like that. So we are done with alkanes and the mechanism of alkanes. Uh, just give me like 30 seconds. Let me talk to my boy.
Okay.